Hi class, this is Mrs. Youngman and today we are talking about symmetry, and I actually have a very special guest here today. Bryce, go ahead and say hi.
Hi.
Hi, Bryce is going to help me because he's been learning about line symmetry too in his class. So you need to know that line symmetry is when you can have something reflected in a line and it appears that they overlap. The biggest thing you need to know here is that it has to be reflected in a line, and that line is the line of symmetry. It's not necessarily that it connects them and makes two congruent shapes, as we'll find this first example here. So Bryce, how about you look at this first example of this parallelogram? Does that one have line symmetry?
No.
Why not?
Because if you would put that one is down that way, and that one is down that way.
Okay.
And that one, see, it doesn't look like a square, or this doesn't look like a square.
So what he's pointing to on the screen that you can't see is he says if you draw a line down like this, if you were to reflect it, it would actually look kind of backwards. So this one here actually does not have line symmetry. This is not a line of symmetry because it's a parallelogram. That doesn't work. Okay, Bryce, what about this rectangle? Does this rectangle have line symmetry?
Yes.
How many lines of symmetry, Bryce?
2.
2. Where are the lines at?
If it's long and you would do that, then it is it 2 more.
Yeah, then they're even on each part, right? And if you were to reflect it, it'd be the same. And there'd be another line right there, wouldn't there? Do you want to show them with your piece of paper?
Yes.
Okay, Bryce, now you're on.
See? And it's one piece, and if you would cut it in half, it makes 2 pieces.
Good job, Bryce.
And if you would go right here, then it's still one piece, but you cut it in half.
Good job. Okay, Bryce, what about this pentagon? Does this have line symmetry?
Yes.
How many lines?
1.
1. It's kind of right, straight, vertical down through the middle here, isn't it? If this had been a regular pentagon, you would have more, but because it's a little kind of shortened than a regular pentagon would be, you would just say that it has 1. And then this one here, Bryce, this has a whole bunch, doesn't it? They're already drawn in. Do you remember how many lines of symmetry this one has?
7.
7 lines of symmetry. So your job for the directions will be to tell how many lines or to draw them in. If you were describing this, you could say 1 vertical line. Or this one here, you could say it has 2 lines. Once in a while, students think the diagonal lines work, but it's kind of the same reason as for this parallelogram, why those aren't actually symmetrical. So for rotational symmetry, what we're talking about is we're talking about rotating around a central point. And when you rotate around that center point, it needs to map onto itself. And we're never talking about 360 degrees. Everything will map back onto itself at 360 degrees. It has to be some increment less than 360. So for example, the square here is the center point for the square. This would be 0 degrees at 45. So for the square, this would be 0 degrees. At 45 degrees, you see how it's not quite back onto itself the way it's positioned in this first one, but when it hits 90, it looks exactly the same. Again, when it hits 180, it looks exactly the same, and at 270, it's exactly the same. 360 would also be, but we don't need to include that because everything would have 360-degree rotational symmetry if we included that. So some of the things that the questions are going to ask you to do for rotational symmetry is describe the order and the magnitude of the symmetry. The order is how many turns, and for example, for the square, it's talking about how many turns it would take to get back to the original. The square would be 4 turns, so the order would be 4. The magnitude is how many degrees each turn would be. And I'll just write for each turn. So the magnitude is always going to be 360 divided by whatever the order is. So for example, for that square, the magnitude would be 90 degrees because you have 4 90-degree turns to get that square back to its original position. For these examples, it says state whether it has rotational symmetry, so we have to write either yes or no. If so, copy the figure, locate the center of symmetry, and state the order and magnitude. So if we're going to say no, we can simply say no, but if we're saying yes, we have a few other things we have to do. So for this one here, this would have rotational symmetry. The center would be right there in the middle. And then the order, usually the easiest way to find the order, at least if it is a regular shape, is just however many sides or however many angles that regular shape has. So the order for this one would be 6. And then the magnitude, remember that the magnitude will always be 360 divided by the order. So in this case, 360 divided by 6 is 360 divided by 6 equals 60 degrees. For this next one, you're actually not going to be able to take this and rotate it to get anything to map onto it exactly the same, so we would just say that this one does not have rotational symmetry. This one here kind of reminds me of like a flag. This would have rotational symmetry. The center would be here, and if you were taking this point and going to that point, you could make 2 turns out of that. So I could say yes, the order is 2, and the magnitude would be 360 divided by 2, which is 180 degrees. For these next ones here, these flowers, this one, assuming all these petals are exactly the same size, which it's kind of having you assume, yes, it would have rotational symmetry. If you thought about like a dot at the end of each of those petals, you see that there'd be like 5 equal parts, or you could do like 5 partial turns. So the order would be 5. And for the magnitude, you might need to grab a calculator. It's going to be 360 divided by 5, which is 72 degrees. For this next flower, hopefully you can tell that some of these petals are a little bigger than others. So if you think about like what it's going to take to go from one to the next, these would be your rotational symmetry turns. Yes, this would have rotational symmetry. The center would be right there in the middle. The order of this one would be 3, and the magnitude of it would be 360 divided by 3, which is 120 degrees. And for this last one, this one here has line symmetry, but it does not actually have rotational symmetry. If you took that and like turned it upside down, the bigger part would be at the bottom. So you could just say no, that one doesn't have rotational symmetry, and you don't need to answer any other questions about it. And then the last pieces of vocab here, we have plane symmetry, which I kind of think of it as like the line symmetry. But for three-dimensional objects, this is where you could have a plane intersect the shape, and not only does it make it into like two congruent shapes, but they're like mirror images of each other. This is where a plane intersects the shape, and not only does it make two congruent parts, but they would be mirror images of each other. Axis symmetry, I kind of think of this as the rotational symmetry. Again, but for three-dimensional objects. Axis symmetry would be some sort of line that the shape can turn around. And probably the best example of this would be a lathe that people use to cut wood when you like turn table legs or whatever. I'll show a little video clip here. So you can see from that it's turning, it has that axis of rotation that it's spinning around, and then people can use that to do the carving or whatever they need to do as they're spinning it. Okay, so then for these last examples, we have to tell whether it has plane or axis symmetry, both or neither, and it says to ignore the stitching and the like specific markings and stuff. So looking at this football, it would have plane symmetry. You could either like take a plane and split it like right through there, right through the stitching, or you could take a plane and cut it right in half that way. If you ignore the stitching, then it could also have axis symmetry. If you assume that like the line that goes through the middle of the football here is the axis, it's actually what football players, as long as they throw it well, kind of spin it on that axis as they throw the football. So I would say that that football has both plane and axis symmetry.
First play from about the 12, and there is Vic, as you talked about, John, rolling and launching downfield for Deshaun Jackson, who accelerates, caught the opening play, and all the way for a touchdown! 88 yards!
For this glove, because of the thumb, it wouldn't have plane symmetry, because if you like, split it this way, then you have like the fingers on one side and the opening on the other. If you tried splitting it this way, again, you have like the thumb on one. So would not have plane symmetry. It wouldn't have axis symmetry either. So I could say that this one is neither. For this helmet, it would have plane symmetry. You could take a plane and kind of cut it right through this way. But if you tried to spin it around, the axis symmetry, if you kind of spun it this way, you'd have like the top of the helmet at the bottom. Or if you tried spinning it like back to front, you'd have the face guard in the back. So this would only have plane symmetry. And for the baseball bat's a lot like the football. That would end up having both. There would only be one axis, and it would be here just like that, like that lathe would spin. And it would have a lot of different planes, but it wouldn't be this way. The planes would cut through here. The reason I say there'd be a lot of them is because if you rotated that bat just a tad, you could have another plane. If you rotated around, you'd have another plane. So this one would have both. I can show you more examples of 3D things in class and point it out a little better. It's always hard to do 3D things on this, two-dimensional piece of paper. So if you need more examples, just let me know, and I look forward to helping you guys with this in class.